Hello, my name is Chamal Tendakun and this is the 2D airfoil testing lab group 3. I'm going to talk about the main objective of the lab and the procedure of the lab. So the main objective of the lab is to measure the sectional lift and the drag coefficients of the S305 airfoil across 16 angles of attack and 1 Reynolds number. We also compare the results obtained to the published NREL data in this lab. Thank you.
Hi, I'm Philip Snyder, and the airfoil that we actually tested in this lab was the AeroLab3 airfoil. It was designed by Dan Sommers in 1988. It has a 19.7-inch chord and a 2.6-inch max thickness. When they were first designing this airfoil, there were two main design objectives. One was to achieve a relatively low maximum lift coefficient that didn't decrease with transition fixed near the leading edge on both surfaces. And the second objective was to obtain a low profile drag coefficient over the range of lift coefficients from 0.5 to 0.9. And this comes into play for the lift coefficient versus drag coefficient graph. It should look similar to a bucket turned on its side, and this is called the laminar bucket. And it allows for very little drag over a wide range of lift coefficients, but drag increases very quickly outside of this bucket as the boundary layer transition moves quickly towards the leading edge of the airfoil. And so while we tested this airfoil in the lab, we used 34 pressure taps. 17 were on the top surface and 17 were on the lower surface. And this allowed us to obtain pressure data along the length of the airfoil. And we subsequently used this data to get the pressure coefficient and lift coefficient data that we ended up graphing. And you will see those graphs later on in this presentation. Thank you. Okay.
So for the procedure, first the S305 airfoil was inserted to the wind tunnel test section, and the necessary apparatus were connected in order to carry out the experiment. Then, under the recorded lab condition, the velocity was increased to produce a Reynolds number of 700,000. All the initial value data was recorded once the airfoil was rotated into the first angle of attack position to be tested. Then, we obtained the pressure values from the manometer. After that, the hot wire probe was moved using the stepper motor controller so that the probe was 24 inches above the floor. Using that view, the average velocity was recorded every 0.125 inches to obtain the adequate resolution of the airfoil wake. And we also use lab files containing the time average data to calculate the necessary criteria. Thank you.
Hi, my name is James McGovern, and I'll be presenting about how we found the coefficients of lift throughout this process. So as we talked about earlier, there are 34 pressure taps across the bottom and top of the airfoil. And using the difference in the pressures from the upper surface and the lower surface, we integrated across the surface in order to find the CL values. To do so, we use these equations rather than an integration to do this. So we found the CP for the upper and lower surfaces, converted it to CN, and ultimately converted that value to the coefficients of lift necessary. To do this, we found the pressure values using the manometer, as seen on the right in this picture, and we adjusted the angles using the alpha disc as seen on the left here. By doing this, we produced a CL graph that we used for all the following data. Thank you.
Hi, my name is Zach Rollman. So to determine CD, our method was integrating the wake profile using Simpson's rule. So first we extracted the Y location and hot water velocity data from our lab results. And a dynamic pressure, a local dynamic pressure value was found for each data point using the Q equals 1/2 rho V squared equation. And then to integrate, like I said, using Simpson's rule, those Q local points were plugged into the f of y function displayed here. And all of those data points were plugged into these constants S1, S2, and S3. Those constants were used in this formula at the bottom, along with the chord and height. This is a picture of the hot wire used to obtain the hot wire velocity data. So getting into our results. First, we plotted the velocity profiles. On the left, you can see just our personal data from our lab. We have the green is -6 angle of attack, and the orange is a +13 angle of attack. You can see with the +13, it's a more full velocity profile, and the velocity is lower near the hot wire in the middle. And on the right, you can see our full class data, and you can see the trends as you go through the varying angles of attack.
So from the CL data that we gathered earlier, we were able to produce a CL versus alpha graph as seen here. The comparative graph from NREL is seen on the right. Although our data does not fully line up, you do see a general trend that is congruent with what you usually find from a coefficient of lift graph. Some of the errors in the data may be attributed to calculation errors within Excel or misplaced data. From the CL data in the process, we also found the coefficients of pressure. So as seen in this graph, we have the coefficients of pressure for the upper and lower surfaces for both the 2 degrees that we tested in our lab section. On the right is some NREL data for various inclinations. Our data, as you can see, is comparable to the NREL data and is seen to have the same trends. Although there are some differences along the leading edge, the overall trends are what was expected from this test.
My name is Ashley Ditto. This is our CL versus CD graph. It takes on a similar shape to the NREL data, but due to our error in CL, as previously mentioned, we get data points a little different than the NREL data. This is our CD versus angle of attack graph. It follows the correct shape, the bucket shape, because we know that as angle of attack approaches 0, CD will decrease. The CD values below 0 may be due to human error, as we know it's not supposed to be below 0. This is the CL over CD versus angle of attack graph. There may be errors in this graph as well because of our previously mentioned error in CL. And for conclusions, the pressure taps were located at the trailing edge, which may have given us the less accurate data for the leading edge. And while we were calculating the CL values, they didn't reach the expected max of about 1 due to the mistake in processing. And although our CL data was disfigured, the charts for the other graphs were still relevant.